Lastly, and very quickly, we need to talk about a few more things about gravitation, and that is about this idea of the gravitational constant. So this happens a lot in areas of science. Newton discovers this constant. He calls it the universal gravitational constant. In effect, it's a number that helped all the numbers work out right. Newton knew that gravity was based on mass. He knew that gravity was based on distance between the objects. But the numbers worked out if you always introduce this one particular number. And that number is 6.67 times 10 to the negative 11th. If you're a little hazy on your scientific notation, you should know that that's a really, really super duper small number. It goes in our gravitational equation right here. It's capital G. I'm going to tell you more about this equation in just a minute. There's no math to this. We're not going to actually use this equation. We could, but we're not going to in this class this year. But it's a really small number. If I write it out in regular notation, I get 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10 zeros with a 667 behind it. That's crazy small. The reason I bring that up is because that really small constant indicates the relative strength of gravity, which is very weak, which you might not have predicted. You've learned a lot of new things about gravity today. Everybody thinks gravity is really strong. Everybody's gotten hurt because of gravity. Gravity keeps planets in orbit. Oh yeah, you need a mass as big as the stinking moon to notice gravity. Like I said earlier, you don't notice gravity between you and the person sitting next to you because your mass isn't big enough. Really, it's because the force of gravity is very, very weak. You need a mass the size of a planet for gravity to really take any kind of effect at all. So gravity is a very, very weak force, actually. And again, the relative size of this constant, there we go. The relative size of the constant tells us that. Now, here's the equation, the gravitation equation that Newton came up with. This is our constant. M1 and M2, those are both masses of the two objects involved. Remember, gravity is a bidirectional force. We have two objects. We need the masses of both of them, and those masses are going to be multiplied. Divide by r squared. Notice that r is the distance between the objects. You might be thinking, well, why do we use r? The answer is because Newton comes up with this while he's looking at the orbits of planets, and he used the word radius. We're going to call it the distance between the objects because, again, it's not just orbiting bodies. It's any gravitational force between any two objects. So the gravitational force is calculated by taking that little bitty constant, multiplying it by both of the masses, and then dividing that by the square of the distance. We're not going to do that math, but there's a few things that you need to know that this equation tells us. The first thing it tells us is that the force of gravity is determined by two things. Number one, the product of the masses. Product means multiply. They both come into play in this. It's not one or the other. We multiply both of their masses. That's one thing that determines the force of gravity. The second thing that determines the force of gravity is the distance between those two masses. Now you might say, well, why doesn't the constant determine that? We don't consider the constant to determine the force of gravity because the constant never changes. The mass and the distance are the things that can be variables. So let's look at these things in turn. First of all, the mass. You need to know, you got to know this, write this down, that the force of gravity is directly proportional to the product of the masses. I know that because the product of the masses is in the numerator, it's on the top. Remember, we've talked about the proportionalities when we talked about Newton's second law equation. When we have an equation that's set up this way, where we have one variable that's equal to a fraction, any variable in the numerator is directly related, directly proportional to this variable. So mass is directly related to the force. That means the greater the mass, the greater the force. If either of those masses increases, then the force is going to increase. Directly means they both change in the same direction. The opposite is true as well. Smaller the mass, the smaller the force. Here's an example of that. If you go to the moon, you will weigh less on the moon, and it's not because you lost mass. It's because the moon has less mass than the Earth. It has about 1/6 the mass of the Earth. So you will weigh less on the moon. This equation will come out to a different number simply because one of these masses decreased. So if on Earth, let's say your mass is 10 kilograms on Earth, which it's not, but let's say a 10 kilogram mass on Earth multiplied by the mass of the Earth. This is not the mass of the Earth. It's way bigger than this, but let's just assume that it is. If the mass of the Earth was 6,000, 10 times 6,000, we get 60,000 for the product of these masses. On the moon, your mass is the same, but the moon has 1/6 the mass. So 10 times 1,000 is only 10,000 for the product of these masses. That's the reason why an astronaut weighs less on the moon. That's the reason why when they jump up, they come back down very, very slowly. They do come down. There is gravity on the moon, but there's less because the force of gravity is directly proportional to the product of the masses. If the masses change, the force of gravity changes. The second thing, force of gravity is inversely proportional to the distance between those masses. Inversely means they change in opposite directions. So if r goes up, if the distance goes up, which means the objects are getting farther and farther apart, as the distance increases, the force of gravity decreases. And that should be intuitive, that the farther apart we are away, the farther apart two objects or two planets are, whatever, from each other, the smaller the force is between them. Opposite is true. The closer they get, so that's distance decreasing, force increases. The force of gravity increases the closer those things get. Example, we fall toward the Earth, not the sun. When you jump up, if the sun is directly overhead, when you jump up, you aren't immediately sucked toward the sun. Now, the sun does exert a force on you. There is a gravitational pull from the sun, and we know that because the Earth orbits the sun. So there's got to be a gravitational force on us as well. The reason we only experience the gravitational force from the Earth is because we are so much closer to the Earth. That's why its gravitational field is greater for us. And another really important point about this equation, changes in distance have a much greater effect on the force than changes in mass. And the reason for this is because distance is squared in the equation. In other words, what this means is the fastest way to change the force of gravity between two objects is not to change their masses, but it's to increase or decrease the distance between them, because that increase or decrease gets squared in the equation. It magnifies the change. So changes in distance cause a much, much greater effect on the force of gravity.